So now we're going to talk about horizontal asymptotes. And it has to do with the degrees of the polynomial in the numerator and the denominator. So remember our definition for a rational function, and I'm not going to write the whole thing out, but it's like a sub p x to the p plus a bunch of other stuff over, and then it was b sub q x to the q, right? Plus a bunch of other terms. Okay, or some other terms. All right. So that's what we have for the definition of a rational function. The horizontal asymptotes are based on the degree and the leading coefficients, okay? Or, yeah, the leading terms. Okay, so in case 1, if q is greater than p, so this will be case 1. I guess I should, well, I should move it over. But case 1, q is greater than p. If that happens, then your horizontal asymptote is at y equals 0. Now, vertical asymptotes, you can have a bunch of vertical asymptotes. You can only have one horizontal asymptote, okay? So that's all you get. And the horizontal asymptote is just at the, it's right on the x-axis, y equals 0. That's how we write it. And that occurs if the degree of the denominator is bigger than the degree of the numerator. Okay, so it's going by those exponents, the exponent here and the exponent here. Okay, case 2. In case 2, what happens is the degree of the numerator is 1 more than the degree of the denominator. Okay, so when that happens, we don't get a horizontal asymptote, we get a slant, what's called a slant asymptote. So an example would be like if you had f of x equaling 3x to the 4th plus some stuff over 2x cubed plus some stuff, that's going to have a slant asymptote, okay? And I can show you how to find the slant asymptote. They give you an example in the book. They have a function f of x equals 3x squared minus 2x plus 1 over x minus 1. And what you have to do is you have to use long division or division. Now in this case you could use synthetic division because the denominator is linear, but sometimes they're not. Like in the little example I had above, you would have to do long division. But here we can use the synthetic division. So we'll go ahead and do that. Okay, it has a remainder of 2. We don't really even care about that. What we care about is this 3x plus 1. That is the slant asymptote. When we write it as an equation, y equals that, that is the slant asymptote. You see it's linear. Okay, and so you can graph that line, but you'll make it a dotted line because it'll be an asymptote. Okay? And that's what happens when the degree of the numerator is 1 more than the degree of the denominator. Now you might be saying, well, what if it's 2? What if it's 2 more? Then we don't have a horizontal asymptote or a slant asymptote. Okay? I don't know that they mention that in this book, but that's what happens. So, case 1, case 2, case 3. Okay, in case 3, the 2 degrees are the same. So P equals Q. Okay? So maybe you have something like g of x equals 5x cubed plus a bunch of stuff over 3x cubed plus some other terms. Okay. When the degrees are the same in the numerator and the denominator, what you do is you take the leading coefficients, and that's going to make your horizontal asymptote. So the horizontal asymptote here is y equals 5 over 3. Okay, so we're making horizontal asymptotes. Those are horizontal lines, and so you just have y equals a number, except for the slant asymptote. That's why it's called a slant asymptote. Okay, and so you get y equals 5 over 3, and that's where your horizontal asymptote would be. Okay, so those are the three cases. Either P is less than Q, or the degree of the denominator is greater than the degree of the numerator, or the degree is, case 2, the degree of the numerator is just 1 more than the degree of the denominator, or in case 3, the two degrees are the same. Okay? And so those are how you find the asymptotes. So you might want to put something like that on a little card to help you remember, because it's the three different cases. And sometimes it's hard to remember that.